Hello and welcome back to Calculus 1 for one last time. This is it, right? 5.5, use substitution. The most important integration technique in the galaxy because it's the most frequent and the one that will make or break for Calc 2. So, what is the U sub? U sub is the technique that it's backwards chain rule, which is why this technique is so important. And the U sub is used when you don't have the basic integral, but you can transform your problem into a basic integral by using U substitution. You are familiar that the integral of x squared dx is x cubed over 3 plus c. You're familiar with that. Actually, I'm going to go with x to the 20th and then have this as 21 because that's easy. So x to the 20th dx is equal to x to the 21 over 21 plus c. You know this already, right, from 4.9. There's nothing special about this. So now the question is, what is the integral of x plus 3 raised to 20 dx? You have a choice. Go ahead and FOIL. I'll wait, right? You have 20 of these parentheses. They all multiply each other. So eventually, by tomorrow 4 p.m. you'll got it, right? You'll have it. And then you get to integrate each one of those and so on. So is there an easier way? And the answer is yes. If you put in a little bit of attitude into this and you just say, if this was just like one variable raised to the 20, I would have an easy problem, right? So how about you transfer that negative attitude, the nasty attitude, right, into something positive and constructive, right? If this was just, you create that u equals x plus 3, right? So that's constructive. So now you replaced your x plus 3 with a u, and now you have u to the 20th, which is great. We can integrate that. But then the problem is that you can't have u over here and have x over here. So you have to change that as well. And the trick is to differentiate this and then move dx to the other side, just like you did for differentials. So now you have all of the replacement parts. The x plus 3 changes into a u, and the dx just flat out changes into du. So now you have the integral of 20 u to the 20, which is u to the 21 over 21 plus c. Right? And then you have to go back to x variable, right? Because no one cares about u. No, I'm serious, right? No one cares about u because it's the variable that the problem was posed in was x. So we replace u with x plus 3 to the 21 over 21 plus c, and then we're done with the problem. Did this make sense? coming up. This is one of those. Thank you for having this. So we know that if we have x plus 3 squared, we're just going to square it and integrate each term. Easy peasy, right? I do not want to raise this to the 20th power, therefore I am going to try and find the easier way to do this. So I define whatever is the unnecessary mess. I define that as a u, and then go through calculations, and then we replace u back with what u was, because your final answer here has to be represented with the variable that the problem had originally. Let's take a look at more examples. Say you have the integral of x sine x squared dx. So, is this a basic integral? No, right? Because it has a polynomial, and it has a trig function, and the trig function is not something that is just so easy, right? So what do? I go and I say, is there a function that has the derivative floating about? And the answer to that is yes. X squared has this x as its derivative. I know it's 2x, but we can fix that. We can work with that. The most important is the variable part. That's satisfied. So if I define my u as x squared, then my du over dx would be 2x. And then I shift my dx to the other side, I get 2x dx. Now you will get used to go to this step right away, where you just put dx immediately on the other side, but I still need you to know where this comes from, so it's not just something that you can avoid, because this dx is supposed to replace that dx. So you can't just skip on it. So now, if I am looking at what I have for my substitution, and I'm looking at what I have, so I'm cool there. Also, x dx. Oh, there's the x dx. Nice. The only issue is this half. This 2. I don't have a 2. So I can move the 2 over here and make it a half. So I'll be replacing my dx with du over 2. So that's one option. Or I will say I have x dx, I don't have a 2. I'm going to put the 2 in and balance it with a half on the outside. That's my favorite way. But there is nothing wrong with writing du over 2 is equal to x dx, and then writing this as du over 2, and then when you take this in front, it will be still 1/2, right, when you take it from here and push it up. So it doesn't matter. So this is what I have done. Actually, I'm going to go with the red on this. So 1/2 and 2. So now I have 1/2 sine u, and x dx, which is orange stuff, changes into du. I'll put that orange. So you know which way all of this traces. Guys, I have a basic integral. What's the integral of sine? Very good. Plus c. Now remember, we have to go back to our original variable, so -1/2, cosine of x squared plus c. And that's the answer. Now let's say you care. You want to check. What should you do? If you want to check, someone just say it, please. Take the derivative of this, yes. Previous lecture, Fundamental Theorem of Calculus, says that if you take the derivative, you go back to the original one. So let's see. What's the derivative of negative 1/2 cosine x squared plus c? We copy negative 1/2. The derivative of cosine is negative sine x squared times the derivative of the inside, which is 2x, and then plus 0 because the derivative of c is a constant, right? It's 0. So now you have negative and negative cancel, 1/2 and 2 cancel, and what's left behind is exactly what the problem was. X sine x squared, which matches that, and we are 100% sure that our answer is perfect. So you can check. If you care, you can check. Fair? Hopefully. Let me give you a problem or two to try on your own. So how about integral of cosine to the 9th power x times sine x dx? Think about that. So what's my u? What has its derivative laying around? Sine x. No, cosine x is the u. Because cosine x is the one that it's raised to the 9th power. The derivative of cosine is negative sine. Then you put the x. And you don't have a negative, so you fix that. Put the negative in and out. They cancel each other out anyway. And now you have negative and cosine dx. That's your du. And your cosine to the 9 becomes u to the 9. So this is the whole method. And we transformed the entire trigonometric integral into a basic polynomial u to the 9 thing. So nice. And we now have negative u to the 10 divided by 10 plus c. And then you go with, I don't care about u, I care about the x. So you replace u with cosine x, plus c, and you're done. Cool, huh? So let's see another one. Integral of, let's say, x squared e to the x cubed dx. This is from the book. So what's the u on here? You always go with the logic, what has derivative laying around? What has the derivative laying around? What is the function? What is the derivative? Look at the mess. What's u? U equals? So how many functions do you see on a pile over here? All together. How many? 1, 2, 3, right? So you have three functions. So which of the three functions has the derivative present? X squared, the derivative is 2x. Do you see x anywhere? No. So x squared is not. How about e to the x? Well, e to the x has itself as a derivative. I only have 1 e to the x. So no. What's the derivative of x cubed? 3x squared. There's x squared. Yes, so that's the one. So x cubed, which means du is 3x squared. The x, I need a 3, so we'll fix that. And now I have 1/3 integral. Here's my orange. 3x squared dx is the du. And what I'm left with is e to the u. So 1/3 integral of e to the u is e to the u plus c. And then we go back to our original variable. And the problem is over. Ta-da! Now, in my humble opinion, I would say straightforward. All I need to do is to hunt for function derivative pair. I'll write that here in blood. Easy peasy, because all I have to do is hunt for function derivative pair. Function is going to be my u, and this will be du. Awesome. Done. Every problem done like that. Now, what do you have to be good with? You have to be good with derivatives, obviously, because you need to spot the function and its derivative. Now I'm going to go back to this problem that we just covered with this now knowledge of what to look for. And as I said, look for function derivative pair. Function is the one that you will differentiate to get. So function is the one that's going to be u. So if I look at this, I said I have x squared as one of the possible functions that I can pick. Remember, you are picking u. It's not given to you, right? Integral is given and that's it. You are picking a u value. You are picking your u value in Calc 2. You are picking your u value in Calc 3. You are picking your u value in differential equations, right? When you take, if you take a thermodynamic class, let's say, right, for mechanical engineering or chemical engineering, you are picking your u's for all of those integrals, right? You are looking at this problem and you say, okay, I see three different functions on a pile. I see function x squared. I see a function that I can call e to the x. You don't even have to call it e to the x cubed. You can just call it e to the x because it's a composite function, right? So I see a function x squared. I see function e to the x. I see function x cubed. So I have three functions. Which one out of those three has its derivative present? X squared, the derivative is 2x. We don't have to worry about number 2 because we saw that we can fix that. So function x squared has its derivative x, and I don't have x laying around. So if I put x squared to be u, I won't be able to deal with e to the x cubed, plus I don't have extra x for du, so x squared is a bad choice. How about e to the x? Well, the derivative of e to the x is another e to the x. So if I take one e to the x and I replace it with a u, I don't have another e to the x for du, and I still have x squared floating around, so that's bad as well. The only one by process of elimination here that is left is x cubed. Now, if I take the derivative of x cubed, I get 3x squared. Yes, because I have x squared, right? So you are looking for function derivative pair. Function is going to be your u, and that's the one that is getting differentiated to get the rest of the problem there. Now, as you can see, we never use the e for anything, so that's the one that's, that sticks around. So in some problems, when you do use substitution, some of the functions are going to stay around, but they are still going to be manageable. And other problems, all of the functions go away. Like this problem. You see that both cosine and sine went away because I picked cosine to be u, and that was raised to the 9 power. So cosine to the 9 now becomes u to the 9, and the sine was in the derivative, so that went and was absorbed by du, and there were no cosines and sines. But the problem right before that one, sine stayed in the problem because, again, it was the game of x's. The derivative of x squared is x. So I never used sine in any of the substitutions, so sine stayed to float around. So these are like two different flavors of what you can get. Like one would be completely taking out all of the other functions, and one would, and the other ones would still have some portions of the original problem float around when you do the u sub. So now, that being said, you are constantly hunting for function derivative pair, right? Function derivative pair. So let's take a look at another two examples. Let's say you have integral of 3 divided by x ln 4x dx and integral of x square root, let's actually do it this way, x over square root of x squared plus 5 dx. Try that. I'll go check something. I'll be right back. I'm going to fill the water. Okay. So let's see. The first integral. What is our u?
ln x.
Excellent. Why?
Because there's a 1 over x.
Excellent. You are looking for function derivative pair. U equals ln x. Because there is 1 over x present. So du is 1 over x dx. We kick 3 outside, right? And then what you have inside is 1 over x dx. So here's times 1. X dx. That's going to be your du. And you have 1 over u to the 4th. Because ln was raised to the 4th power. So the integral that you are solving is 3 integral u to the minus 4 du. And that is 3 u to the negative 3 over negative 3, plus c. The 3's would cancel, and you would get negative 1 over ln cubed x plus c. Right, negative 1, because you have the negative still floating around, and you have your negative 3 exponent pushes u cubed into the denominator, and then it's ln cubed. Great. How about the other problem? What would be u for the other problem?
X squared. Yeah.
Nope. What's the u for second problem? What do you have? X squared as well? Yeah. Yes. X squared plus 5. Then the du is 2x dx. I don't have a 2, so I'm going to fix that. And then we go on with the rest of our life. 1/2 integral of 1 over square root of u du. Because the, wanted that orange. Does it make sense?
Yeah.
Great. So now I have 1/2 integral u to the negative 1/2 du. When I integrate, I add 1. So that's going to be u to the positive 1/2 divided by 1/2 plus c. These 1/2s will cancel completely, because 1/2 divided by 1/2 is 1. And all I have is the square root of u plus c. Now, I don't care about u, I care about the x, which means we put x squared plus 5. Plus c, and we're done. So that's the answer. Now, I hope that as you do a whole bunch of homework, you will find this very structured eventually when you start seeing the patterns, and when you get good, that's good as GUD, when you get good with figuring out function derivative pair, and you'll be able to get that. Now, is this it? No. There is a second part to this, which has you calculating definite integrals using u sub. So now we get to add another component, so u sub for definite integrals. This is still the same lesson as just another part. So let's, I'm going to, now I have to be a little bit careful. I can't put whatever. So we have already seen a problem similar to this. Sine to the fourth x, cosine x, dx. But now we have from pi over 6 to say pi over 3. So now we have limits because we have a definite integral. The question is what to do with that. Well, first off, you have the u sub. When you do u substitution, you are changing all of your x's to u's. Your limits are also x's. So what has to happen there? Common sense. Right? If the u substitution changes all x's to u's, and your limits are u's, x's as well, they need to be changed into u's. So we start by figuring out the u substitution, and then we'll do all of the transformations: integral transformation, dx transformation, and limits transformation. So we did everything up to the point where we just did not have limits before. So it's the same idea. We just need to change the lower limit and upper limit, and we are done. So I start with, what's my u? Cosine x. And what's my du? Negative sine x dx in that case. So now do you see how I still have three signs that are issue? Because if I use one sign and dx, and I replace this with u, I still have sine cubed to deal with because I only used one up for dx, right? So what happens when you are not able to substitute? You switch it, right? Because it was bad choice. So sine x, and then have cosine x dx here. So now it becomes the integral. Sine is u to the fourth, and then the cosine x becomes du. Well, that's great. But I have also these limits floating about. So now u1 is going to be sine of pi over 6, which is the bottom limit, which is a half. So the limits change using the regular formula, right? Sine x, whatever your u substitution is, you use that formula to change your upper and lower limits of integration. So sine of pi over 3 is root 3 over 2. So I have changed my integral from trig now completely into polynomials. Now I have u to the 5 over 5 computed from 1/2 to root 3 over 2. No plus c now. This is a definite integral. It's going to give us a number. 1/5. And now I have root 3 over 2 to the 5th power minus 1/2 to the 5th power. One-fifth, I have 9 root 3 divided by 32 minus 1 over 32 when I compute these fifths. And finally, this is 9 root 3 minus 1 divided by 160. Because 32 times 5 is 160. You have a common denominator of 32 and then times 5. So now your answer is a number, right? The answer is a number because we started with a definite integral. So now what is the only thing that is new? This. You using the whatever your u sub is to transform the limits so that you can plug everything in and calculate. Let's see more examples of this. Say you have 62. Integral 0 to 1 over 8 of x divided by the square root of 1 minus 16x squared dx. Think about, you first have to come up with u and du, and then you can change your limits. What's the u? Anyone? Yes, 1 minus 16x squared. Actually, this is a troll question that I put on Calc2 exam. And yeah, du is negative 32x dx. I don't have negative 32, so I'll plug that in. So negative 32 integral, and now I have u to the negative 1/2. That's the denominator. Du. And now I have to calculate these limits. So u1 is 1 minus 16 times 0 squared, which is 1. And u2 is 1 minus 16 times 1 over 8 squared. So 1 over 8, that's a 16. So I have a 16 divided by 8 times 8. So that cancels into a 2, that cancels into a 4, so 3/4. You can use calculator, whatever. I mean, learn quick computing. So negative 32 integral 1 to 3/4 u to the negative 1/2 du. Now, what I see is that the bigger number, larger number, is in the denominator. So negative 32 becomes positive 32 when you swap these limits so you can have them in correct order. So if you need to interchange these limits, then you can do so with the minus and plus in front of the integral, right? So you change to the other whatever you had. So we had the negative in front. When you swap, then another negative is introduced and they cancel out. So now this is 32 u to the 1/2 divided by 1/2, computed from 3/4 to 1. 32 divided by 1/2 is the same as 32 times 2, so that's 64. And now I have square root of 3/4 minus square root of 1. So this would be 64 times square root of 3 divided by 2 minus 1. And you can leave it there. It's okay. You can leave it there. Or you can come up with the common denominator of 2 and then get the 32 again. Maybe that would be a good idea. 32 root 3 minus 2. If you come up with a common denominator, then root 3 minus 2 is in the numerator and 2 cancels. Okay, fine, we can do that. Simplified version. Let's put one more of these and then be done with this. Problem 64 from homework. Integral 0 to the ln of 4 e to the x divided by 3 plus 2e to the x dx. So this one is tricky, right, to find u. What's u? What happened? What's u? If we put the entire denominator as u, then what happens? Yes, so du is just 2e to the x dx. I don't have a 2, but we can fix that easily. And u1 equals so when I plug in 0, 3 plus 2e to the 0 becomes a 5, right? Because e to the 0 is 1. 1 times 2 is 2. u2 equals to 3 plus 2e to the ln 4, which is 11. Because ln and e cancel. 2 times 4 is 8, plus 3 is 11. So now I have 1/2 integral 5 to 11, and then I have 1 over u du. Now, what is the integral of 1 over u? What's the integral of 1 over u? What's the integral of 1 over u? Come on. Uh-oh. Put this one on the final definitely then. What is it? Guys, you gotta know this one. Yeah, ln of u calculated from 5 to 11. So it's gonna be 1/2 ln 11 minus ln 5. And now if you want to be a boss, you put that in a single ln 11 over 5. And that's that. So that's u sub. You go and you find the function derivative pair, you substitute, and if you have limits, you change the limits as well. And then just compute the easy integral. And make sure you know that the integral of 1 over u is ln u, because, or 1 over x is ln x. That one actually pops up a lot in Calc 2, so make sure Make sure you definitely know it. And that's the course. Bye.